Now I want to go through a very, very important concept when it comes to how molecules, covalent molecules, arrange themselves. Keep in mind, covalent compounds share bonds, and those bonds are made out of electrons. So this little bond right here, or these double bonds and these Lewis dot structures, okay, are both negatively charged. They want to get as far away from each other as actually possible. But you're used to looking at data, information, and molecules in 2 dimensions because we write this on a piece of paper or on a board or wherever it may be. Molecules don't live in those constraints. You are 3-dimensional just as molecules are 3-dimensional. And so we have to consider that when you look at what the structure of a molecule looks like in reality, in our 3D reality. So let's start with something simple. If you look at CO2, the Lewis dot structure we looked at last time looks like this guy, right? If you will, I'm going to simplify that. I'm going to say there's an atom in the middle and there's 2 things coming off of it. The furthest distance that those 2 things can get from each other, the happier these electrons that are in these bonds will be. Simply because they're negatively charged, they want to get as far away from each other as possible. It's like putting 2 north ends of a magnet together. They repulse one another. Well, that's relatively easy. We can do that by putting 1 in the middle and doing something like this. Now this is actually CO2. Note that I have a double bond between these. It doesn't matter if you have a double bond or a single bond. The furthest distance that 2 things can get away from each other looks like this. That's a line, right? And so we call that, see how that's a line that direction, no matter which way you go. That is going to be a linear molecular geometry. Linear molecular geometry. Okay. Now, let's consider a central atom with 3 things surrounding it. You might draw this on a piece of paper like this, looking like a T. But is that the furthest away from each other that everybody can get? Because here we've got a 90-degree angle, and here I've got, oh, that's a lot more space. In actuality, the furthest that these 3 bonds can get from each other looks kind of like a Mercedes sign. Okay? It's still in one plane. In other words, it's flat. And these are coming in 3 different directions. This bond angle, in other words, the angle from this bond through the middle here to over here is about 120 degrees. Okay? So those 3 things are trying to get as far away from each other as possible. An example of this would be another thing we looked at last week. Okay, this structure actually only has 3 things surrounding that oxygen. So even though there's 2 bonds here, they're going in the same direction together towards this atom. So there's only 3 things surrounding this central atom. So here's what that structure or model looks like. And yes, there's 2 bonds going towards this oxygen, but it's still flat. Okay? So that's what that guy looks like in 3 dimensions. So next, let's talk about this one. You would think, by looking at this on a piece of paper, that you should have an atom in the middle, top, bottom, left, right. That does not occupy 3-dimensional space, however. When you look at this structure, the CH4, which looks like this, is very similar to what we see up here. Okay? But here's what its structure looks like in 3 dimensions. Let me start turning that. Okay? I can put things down on a plane or flat down on this sheet of paper. Look here. I'm going to slide my finger underneath. See, it's not quite, but okay, maybe I can slide this underneath. See how that goes underneath? No problem. That's because this carbon here does not sit directly on the sheet of paper. The same way that there's space right here, if I lean this up, see how that doesn't sit flat? This forms almost a pyramid, okay? And there's like a surface here that's flat, one to this side, one to this side, and one to this side. But none of those come in contact with carbon. We call this shape tetrahedral, or a tetrahedral molecular geometry. In 3 dimensions, this is the furthest away that these atoms can get from each other, and more importantly, the bonds can get from each other. And that's about 109.5 degrees. As I failed to mention this over here, this guy, right here, is what we call trigonal planar. Planar. And he has about 120 degrees in his bond angles, okay? So that takes us through the first of several molecular shapes. Because before we start looking at polarity, we really need to understand this. When you have 2 things surrounding the central atom, whether they be electrons or atoms, they try to get as far away from each other as possible. By electrons, I mean lone pairs of electrons. We don't have to worry about that here. Just as I showed you, that is a linear molecular geometry. When you have 3 things surrounding a central atom, he would have a trigonal planar molecular geometry. I'm going to skip this next one and come back in a minute. Okay. If I instead have 4 things, that's when we have a tetrahedral molecular geometry, if you have 4 atoms surrounding them. But what happens as we go from CH3 to NH3? If you recall, there's a lone pair of electrons on nitrogen right here, right? Those still take up space in the 3D realm. So in other words, instead of having it look like this, you just don't have an atom right there. Perhaps an easier way to see it, which this is fine if you want to look at it like this, I like to put in what that atom would look like as far as like what its electrons orbitals would look like here. So the electrons live within this guy. These atoms are still here, but electronically there's 4 things surrounding that central atom. So electronically it still has a tetrahedral shape overall. But in reality, if we were to take this away, the shape of the molecule or the atoms is different. They're not flat. They come up a little bit. We refer to that as a trigonal pyramidal structure or molecular geometry. Okay. Now what if you have water? The Lewis dot structure for this looks like this. And just as with the NH3, both of these electron lone pairs take up space. So instead of having one of those off, I take off 2 atoms, or 2 spots, and add where the electrons would be. So see, this is still the same tetrahedral type of arrangement. So if you count 1, 2, 3, 4, it comes from 1, 2, 3, 4. This has a tetrahedral this has a tetrahedral electronic configuration. But if we remove these and just consider where the atoms are located, carbon's right here, here's your 2 hydrogens. This is a bent molecular geometry. It is very important to realize that water has a bent molecular geometry. Here's how much I love this. Water is bent, and that's the reason why you can even be alive. It's so important in so many other things, which we'll look at a little bit next video. So by having 2 atoms, but 2 of those that are lone pairs, this is a bent molecular geometry. In the same way, if you have 3 things surrounding a central atom, 2 of them are atoms, 1 is a lone pair, such as you see here with ozone, we would take this guy and instead replace up here with electrons, or better yet, the electron orbital where those electrons reside. And if we take this guy out, guess what? You're again left with a bent molecular geometry. So bent is possible in 2 different ways. Okay, thank you very much.